Okay, there we go. Looking good. So, hi. Thanks for letting me do the talk. My name is Marcel Ruland. I'm currently a master's student in Coxie. This is my third master semester now, and before that, I did a master in cognition and language in Barcelona, and before that, I did a master in linguistics in Paderborn. So I started in linguistics and then slowly but consistently got dragged more and more into cognitive science. My talk today is absolutely not related to linguistics in any specific way. It's about agent-based modeling. So this is a technique or method I'm very fond of. I very much enjoy using it. Okay, so we might as well just get right into it. So first, what I'm going to do is I'm going to contrast, or basically tell you the differences between agent-based modeling and traditional modeling. I think that's a much more accessible way of explaining it than just having agent-based modeling standing alone. So traditionally, when you create a model, you usually start very simple. So you don't care about details, you don't care about exceptional cases maybe, but you have very few global parameters and you have a very simple model that maybe makes one or two general predictions. And then when they're reasonably accurate, you slowly start adding more and more aspects to your model, and your model will become more and more complex. And this is what you see on the left-hand side, which you also might call a top-down approach. So you start at the general top, and then you work your way down into the individual details and bits and pieces. Agent-based modeling is basically the complete opposite of that. So agent-based modeling starts at the bottom and then works itself up. So you start at the bottom by modeling an individual agent, and I'm going to explain in a minute what exactly that is. Then you give the agent a behavior, and then you basically observe more general principles that show up at the population level. And this is what you may call a bottom-up approach. Okay, so to summarize, the top-down starts at very general principles, and then you go more and more into details and specific cases. And agent-based modeling starts at the individual cases and then works its way up towards general principles. This will become clear when I give you an example. Actually, we have a couple of examples. So an agent-based model generally consists of two main parts. One being the agents for, obvious reasons, and another one being the environment. So the example you have here, I think, is quite accessible. It's basically humans living in a city, and all the individual humans are your agents, and the environment is the city itself. So you have the humans living in the city, the agents living in the environment. And then you can have either what we call agent-agent interactions. So in this case, it would be one human interacting in some way with another human, or agent-environment interactions. So in this case, a human interacting with the city. By the way, if I look to the left, it's because I have two screens, and here I can actually see the chat, but I'm very aware that you're actually over here, or the camera is over there. And the neat thing, or one of the neat things about agent-based modeling is that it allows you, it's not the only thing that allows you to do that, but it works very well with that, it allows you to observe something called emergent behavior. And that's a very fancy word, and what it actually means in plain words is behavior that doesn't really make sense when you're looking at an individual being. So in this case, an individual human may not make sense, but if you look at the population level, then it actually makes a lot of sense. These phenomena can only occur at the level of the population. So I'm going to give you a more concrete example of that. On the left-hand side, it's a picture of a bird. It's a bird, in case you didn't immediately recognize it. And you know how birds sometimes fly in swarms or fly in formations. If you, for example, if you've seen starling formation are very famous and incredibly beautiful. Or you get those V shapes. You get all kinds of formations birds flying. Now, if I give you a single bird and ask you what formation does it fly in, that question doesn't really make any sense, because a single bird by itself isn't capable of forming a formation on its own. It is not defined. It doesn't make sense. But if you go to the population level, so those are swarms of birds, in case you didn't recognize, now it starts making a lot of sense, because we can clearly see that they tend to form groups. I mean, this specific type of bird tends to form groups and definitely show some kind of swarming, some kind of formation. Another completely different example for the same abstract concept is a traffic jam. This is a single car. I know it's a wedding car. It's completely not the point. It's just it was a copyright-free picture I found. Ignore the wedding bit. So it's a single car. And now, if I were to ask you, is this car likely to be in a traffic jam? Does it easily get caught up in traffic jams, or is it very good at avoiding traffic jams? It doesn't really make sense. You cannot answer that, because a single car on its own can neither, it cannot be prone to traffic jams or form traffic jams. It doesn't make any sense. But again, if you zoom out and you look at a population of cars, now you could clearly say that this tends to be a traffic jam, and maybe on the other side of the road, I don't know if you can see that, but it's a little less crowded. And suddenly the concept of traffic jam makes a lot of sense. And a cool thing that we can do with agent-based modeling is that we can see how complex behavior tends to emerge from very, very simple rules. And I'm going to give you three examples, three real-world examples. I mean, they are modeled, but they have counterparts in the actual real world. And what we're going to do is I will explain to you the simple rules of what's going to happen, and then maybe you can have a think of your own, and just think, okay, if we let the model run, what may happen? And then we're actually going to let the model run and see what happens. Okay, we have three examples. The first one is related to ants. So ants look for food. Makes sense. And this is a very simple model. So basically, what happens is the following. The brown circle is the ant's home, and the orange circle on the right is a food source. By the way, if anything is too small, just I keep an eye on the chat. I will try to enlarge things if need be. Then what is going to happen is that a single ant will leave the nest and walk in a somewhat random fashion. You can see the blue line. It's definitely not a straight line. It doesn't really make sense. It's not very effective. It will wander around until eventually it finds the food source, but it's definitely not effective. It's way longer than it would have to have walked. And then all the other ants will follow. And what the ants will do is they will walk in a straight line towards the ant directly in front of them. So if I'm an ant, all I will pay attention to is the ant directly in front of me. I ignore everything else. All I see is the ant directly in front of me, and whatever it does, I follow it in a straight line. And what do you think is going to happen if the leader ant just walks in this seemingly random fashion, and then all the follower ants walk in a straight line towards the ant directly in front of them? While you think of that, I'm actually going to try and set up the model. I mean, this one is already set up. Okay, we're going to go really slow so we can see what's happening. Now, same thing, home on the left, the brown circle, food source on the right. Now, if we go really slowly, you can see the red one is the leader ant, which basically walks around randomly. And then the yellow ones each follow the ant directly in front of them in a straight line. And again, like you've seen on the slide as well, the leader ant is not very effective, but I'm going to speed it up a bit now. But just by this one simple rule, follow whoever's in front of you, they actually get a much more effective path. So if you compare the red ineffective path to the blue much more effective path, this is how they find it, just by following this ridiculously simple rule. Just walk towards whoever's in front of you. That's all they do. And this is actually similar to how real-world ants do it. Now, the second model is a favorite of mine. It's the Schelling segregation model. Thomas Schelling is a social scientist. And again, we have very similar simple rules. This could be a human population, could be basically any population where agents or people or agents can freely choose where they want to move to. Now, the important bit is there is no hostility involved here. The orange and the blue agents get along swimmingly. And every square basically represents one agent, one household, one human. You can choose either of those, works with all of those. They get along well, but they like to live in a neighborhood, the neighborhood being the 9 squares directly surrounding them, with at least 30% of similar agents. So 30%, not that much. If they're happy, they basically stay where they are. If they're not happy, those are the axes, they will move to a new random place until this condition is fulfilled, that you have 30% of similar agents in your direct neighborhood. And while you think, I'm gonna, no, I do not want to save. I'm gonna load the model. And again, enlarge things. Okay, there we go. Now, if we start this again very slowly, you can see like all the unhappy agents move to a random new position until they find one where they are happy. And I'm slowly going to speed up. And what happens are segregated neighborhoods. Now, the key lesson here is, I think, that the underlying rules don't imply any form of hostility or excessive racism. All these things don't really exist in that population. The only thing we said was, I would like 30% similar to me to be in my neighborhood, and that's enough to cause this excessive form of segregation. Actually, if I vamp it up to 50%, you can see what happens then. The effect is much stronger. Like, you know, there are huge blue blobs and huge orange blobs, but there are no mixed neighborhoods. It doesn't really exist, except for here, and even there, like there are empty spaces. There are spaces that no one wanted to take. And I think I'm already going to move to the third one. I think so, because yeah, I think so. So the third one is a bit more complex. We're going to go back to birds. So again, these are our beautiful birds on the right. They have a random position, a random direction, and this time the rules are a bit more complicated. So they will follow 4 rules. We're going to go through the rules, and then we're going to run the model, and you will see what happens. So you're a bird, random direction, random position. 4 rules. The first thing you do is you want to be close to another bird. If you are too far away from the nearest bird, you will change your direction towards it and go faster. Rule number 2, once you are close enough to the other bird, you will randomly try to move a bit left of it or a bit right of it so that your view isn't obstructed, because if a bird is directly in front of you, you cannot see, so you move a bit to the left or a bit to the right. Now, rule number 3, if you're too close to the other bird, you slow down. You don't want to crash into it for obvious reasons. And rule number 4, once the first, second, and third rule are all met, you will set both your speed and your heading similar to that of your closest visible neighbor, okay? Which basically means the closest bird in front of you, because you don't have eyes on your back. I mean, birds probably have a wider radius than we have, but yeah. So think about those 4 rules. I'm going to load the model. I managed to spell V. There we go. Now this one is a bit more tricky with the parameters. We may not immediately see what we want to see. I'm going to decrease the number of birds a bit, and I'm also going to make them a bit larger. Yeah, that should be visible. Now, the birds are following the 4 rules we talked about. And now I'm actually going to let this run really fast because it takes a while to form. Now what happens is that you get this sort of V shape. You can see it here very nicely. I assume that geese, for example, do this. You've all seen birds which fly in the sky in this sort of V shape. And in the real world, there are additional parameters which are not incorporated in the model. Like, for example, there are aerodynamic advantages of flying next to someone else. But we recreated this real-world behavior with incredibly simple rules. And from that, you can actually make deductions that the rules in the real world are not going to be too similar. Sorry, are not going to be are not going to be too different, because this is a very computationally effective way of creating this population level. And yeah, with that, I'm already a single minute over my time, which I think is bearable, I hope. And yeah, I'm going to go back to the slide with the rules, because I think you may not be able to remember all of them. And that's it. That's me done. I conclude. And I'm happy to take any questions. That's okay. I will patiently wait for the questions.
I think you're muted, Marcel.
Oops, okay, now I'm back. Okay, so Alina asked, in which field do you see agent-based modeling, or where do you wish it to see? So for the first question, it's really, really versatile, which I really like. So I'm going to give you some examples of where it's used. You can model cars in a road network, so traffic studies, which actually is a thing. You can model an animal population in a forest. And you can model a virus spreading. You can model pandemics very well using agent-based modeling, even though it's not the only paradigm you can use for that, but it's definitely one. In my master's thesis, I actually looked at aspects of the evolution of modern human language using an agent-based model. It's obviously a bit more complicated than those, but it's the same paradigm. Where I wish it to see, I honestly couldn't think of a discipline where I don't want it to see. That doesn't mean that there may be one where it just doesn't make sense, of course. In which course can one learn this? I wish I could give you an answer for that. Actually, I do not know of a class in Osnabrück that teaches this, but I may just not know it. There are I'm gonna just put some resources into the chat. Maybe there's a way of forwarding them to Twitch. So the software I use is NetLogo, which is really slow but very approachable and very easy to learn. And there is a book which is called Agent-Based and Individual-Based Modeling. And it's by Railsback and Grimm. I think the book is absolutely wonderful. I learned virtually all my agent-based modeling using this book. Would you be confident in drawing conclusions about human cognition based on modeling in emergent behavior? Well, that depends. I think you have to be very, very careful with making conclusions about very complex things, and human cognition definitely is a very complex thing. And I think you can use it as a tool, but I would never make strong conclusions based on an agent-based model alone. I mean, you have to approach this very interdisciplinary. There's that term again. So, for example, I do language evolution, and I use this agent-based model. But there are geneticists doing that part. There are archaeologists, there are linguists, there are psychologists, computer scientists, and in general, try to approach complex phenomena from as many ways as possible, and look at other people who have approached them from different directions. And taking all that into account is, I think, the safest bet for drawing a strong conclusion, even though generally I'm very wary of strong conclusions. Can you link us to your research on language emergence? I can do that. If things go well, it should be available in a couple of days, and then if you're interested, I'm happy to forward it.
Okay. Since there don't seem to be any further questions, thank you very much again for being here and giving the talk.
Thank you.
And